Ladies and gentlemen, welcome to the Hong Kong IE Civil Division event, technical webinar on From Micro to Macro, Advanced Multiscale Modeling of Granular Materials, organized by the Hong Kong IE Civil Division and the Polytechnic University. I'm the MC of today's webinar. We are honored to have Dr. Weijian Liang, who is a research assistant professor in the Department of Civil and Environmental Engineering at the Polytechnic University. He obtained his bachelor in theoretical and applied mechanics from Sun Yat-sen University and his PhD in civil engineering from the Hong Kong UST. His research interests focus on computational geomechanics, including multiscale and multiphysics modeling of granular materials, high-performance computing, meshless approaches, and geotechnical analysis. Without further ado, I would like to invite Dr. Liang to deliver the talk. Dr. Liang, please.
Well, thank you, Fiona, for the kind introduction. And good afternoon, everyone. Thank you for taking time to join in this webinar. And this is Weijian Liang from Hong Kong Polytechnic University. It is my great honor to be involved in this webinar series, especially after a lot of giants in the department. Before I get started, I wish to spend a couple of minutes to introduce the PolyU CE department. CE department enjoys a well-known global recognitions. According to the diverse subject ranking, CE ranks #1 among all universities in Hong Kong. And we are also proudly have 28 CE scholars ranking the top 2% scientists. CE also made outstanding achievement in funding acquisitions. Over the past 8 years, we have won 4 prestigious SIM-based research schemes from the RGC, including Professor Li, Professor Wang, and our President Teng. In addition, we also have excellent performance in other funding acquisitions, such as the Green Tech Funding, Land Conservation Fund, as well as the RGC CRF, as well as the RIF. So far, CE has below academic programs like the undergraduate program, or postgraduate program, and also the research postgraduate program. Over the 85 years history, CEE has nurtured a large number of outstanding alumni, and most of them are playing a key role in different areas of our society. CE also has a very high-end and high-quality facility, including 30 laboratory, 2 workshops, as well as 1 research center in Shenzhen. Wow, that's it. So please subscribe our social media channel so that you could receive the latest news from the CEE. Okay, let's come back. Today, the topic I wish to share with you guys is from micro to macro, advanced multiscale modeling of granular media. First of all, I would like to acknowledge the supervision by Professor Yin in PolyU, Professor Jidong Zhao in UST, as well as the Kenichi Shogai and in UC Berkeley. Also, I would like to thank the fruitful collaboration with my colleague Jidu Yu and Shiwei Zhao in UST. Granular media are very complex material. Just as this comic shows, if we rank the area of physics by difficulty, it would find that the general theory of science is even more harder than the quantum mechanics. And that's not surprise that understanding the behavior of granular media is listed as one of the 100 unresolved scientific problems in 21st centuries by the Science magazine. In computational geomechanics, scholars usually use the continuum approach to study the behavior of sand, especially in the engineering scale and the sample scale. For the continuum approach, they typically rely on a constitutive model such as the Moore-Coulomb and also the modified Kempf model. if more advanced feature need to investigate, so that we need to turn to more advanced constitutive models such as the bounding surface and Simpson, etc. Based on the constitutive model, we need to calibrate those constitutive model parameter by the laboratory element test, and then we can integrate it into the continual numerical approach such as the finite element method, material point method, smooth particle hydrodynamics, and also the paradynamics. But the problem is, how can we obtain a general constitutive model for sand, especially under the situation that the sand grain has so much property from the shape, size, roughness, strength, density, rigidity, and each one of them could affect the collective behavior of the sand sample. This dilemma also motivated the development of the discrete method, such as DM, MD, and non-smooth contact dynamics. For these discrete methods, they could consider the grain characteristics, such as the morphology and the grain size distribution. While for each particle, they will just using the contact model to model their interparticle friction, rolling, and sliding, and even the breakage. For the discrete method, they mainly focus on the sample scale and the particulate scale. That's because for this branch of method, they need to consider individual particles kinematics, so that it's quite computationally intensive, so that it cannot, or it is very hard to apply it in engineering scales problem, such as the landslide, etc. And as you can see, different scale behavior of the granular media are typically considered separately in conventional numerical modeling. Here comes to our key questions. Is it possible to bridge up the multiple scales behavior of granular media? And could we propose a unique framework which is suitable for a wide range of granular materials such as sand and the rock, just like this sandcastle? Are there any approach could help us to directly dive into the particle scale to see what was going on? With this question in mind, I wish to share with all of you that some of our minor contribution to the computational geomechanics. The topic one is a unified MPM and the DM multiscale approach. In the proposed multiscale multiscale approach, we will adopt the material point method for as its macroscopic solver. MPM is relatively new continuum approach, and it adopts particle to represent the whole continuum body. However, it will also rely on background mesh to compute its spatial gradient, so that it can use to update the strain and also update the kinematics for each particle. But different from the conventional mesh-based methods such as the FEM, the background mesh will not deform, so that it will not undergo the mesh distortion issues like the FEM. MPM is quite efficient and quite popular in geomechanics and also in the computer graphic. Here is a very famous animation by the Disney. This is the video clip in the Frozen, and it was rendered or it was simulated by the MPM. So far, there are no available commercial software for the MPM. But in terms of the open source code, we have many choices, such as the CBGO by UC Berkeley and the Darren MPM by Oregon State University, and also the GeoTaichi by the Zhejiang University. While for the mesoscopy, we're just using the discrete element method. which rely on the contact among each particle to reproduce the overall packing nonlinear behavior. In current study, we're just using the open source code yet to carry out DM simulations. And depending on the problem setting, we can just generate a 2D packing or the 3D packing. And in our simulation, we will generate a packing and then use this packing as a representative volume element to replace the role of the conventional constitutive model. So that, which means that as long as we obtain the deformation, we can obtain the response through the DM packing. Here is the overall computational procedures as which is shown in this diagram. Initially, we need to do the initialization. First of all, we just discretize the whole domain by the material point here. Then we can generate a DM packing and attach this packing to each material point in the continuous domains. With this process done, we then step into the main loop. In each step, we can compute the particle incremental displacement gradient, which also the deformation information, right? With that information, we can pass it to the DEM. Then we can share the DEM based on that deformation information. After the sharing, we can homogenize quasi-stress and other microstructural quantities such as the fabric and isotropic, and then pass it back to the material point to facilitate the subsequent computations. Once this step done, so that it can step into another loop or another step. As you may noted, the proposed method has several features. The first one is the proposed method is quite suitable for large deformation because we are using the MPM in the macroscopy so that it will not subject to mesh distortion. And also, in the mesoscale, we are using the DM, which means that all the response of the material is directly obtained or simulated by a very physical-based simulation. With this physical engine or physical-based simulation, we can avoid the phenomenological constitutive model, which rely on very high calibrated parameter or etc. Since another thing is, since this packing will attach to the material points throughout the computation, so that the loading history will be directly reflected or conserved. Since each material point is independent from each other, so that is quite straightforward or is quite suitable for the parallel computing. Let's look at a very simple example. The first one is the biaxial compression. Yeah, this is the multiple simulation of the biaxial compression packing. And this is the macroscopic deformation. And we can also investigate the DM packing here and here. We could find that the packing located in the shear band will subject to very extensive shearing, while for the packing far away from the shear band, it will undergo very minor deformation and even the same as the previous one or the initial state. The second example is the cyclic shaking. This is the, we just put the shot here and then do the simple shear. And on the right-hand side, it shows the shear stress and the shear strain. As you can see, as the shearing continues, the packing will gradually lose its strength. If we look into the microscopic response through the force strain, we can notice that initially, the force strain is strong and continuous so that it can sustain the riding external force. However, after the cyclic shaking, the force strain will become scattered and the force strain will become scattered and discontinued so that it cannot sustain. any external force any longer. Let's look at another case such as the footing and the pipeline. In this case, we did not change any parameter. We only just modify the packing initial relative density. With this modification, we can naturally reproduce the different failure pattern for the footing problem, ranging from the general shear failure, local shear failure, and the punching failure, which also quite kind to the actual setting because depend on the relative densities of variance, the soil will also undergo different failure pattern. Another thing is the offshore pipeline. Yeah, this pipeline will be firstly pushed into the soil and then move horizontally. From this animation, you can also note this approach is quite suitable for large deformation. Another engineering case is the vertical anchor in sand. Anchor is an efficient solution for stabilizing the floating structure in offshore engineering. And in this case, we wish to model the vertical anchor throughout in sand and to see the shore deformation pattern as well as its relationship between the burial depths. This figure shows the breakout factor, which is to be used to measure the bearing capacity of the anchor. And it shows the relationship between the breakout factor as well as the burial depth. And as you can see, when the burial depth is quite small, then its bearing capacity will be increased linearly. However, if the burial depth is large enough, the breakout factor is increasing is not that apparent and even remain constant throughout the as the burial depth increase. This two contour shows the displacement as well as the particle rotations for different burial depth cases. In this, for these cases, we also compare the loose sands as well as the dense sands. From this contour, we can infer that for the shallow packing or for the shallow anchor, all of them will be failure with the general shear failures. While if the burial depths turn to the medium wise, so that the loose case and the dense case will exhibit different failure pattern. For the dense one, it will be failure with the general shear failure. However, for the loose one, it will change to the general localized failure. If the burial depths get deeper and deeper, they will gradually reduce in the rotational shear failure. Yeah, as I mentioned above, one of the advantages of multiscale modeling is that we can directly look into the particle scale to see what was going on. Here is an example. In this case, we just select 3 different packing located at different position of the anchor, and the position is showed in this diagram. Yeah, as you can see, for the packing located behind the anchor, it will be featured by a very weak confinement so that it will not generate noticeable force strain. While for the packing in front of the packing, it will subject to a very intensive compression. While for the packing located at the shear band, it will subject to an extensive shearing. As you can see, this packing is deformed fiercely, become long and slender. We can further conduct more quantitative analysis. Also, for the packing ABC, as you can see, the region A is in the active zone, which is behind the anchor, so that it will be featured by a very weak confinement and its stress state is quite low. while for the region B, it was located at the passive zone, so that it was featured by a strong compression and exhibit a very high stress state. While for the region C, it will be featured by a monotonic increase in difficulty strings. And if we look at its porosity, it will be found that during the later stage of the loading, its porosity will not change anymore, which potentially indicated that the packing here is very likely step into the critical state. Now let's look at the 3D case. Although it is quite conceptually straightforward to extend it from the 2D to the 3D, however, it's quite difficult in the technical aspect. First, if we wanted to extend it to 3D, we have to use more material point in the problem domain, which implies that we will include more DM packing. In another aspect, for each packing DM simulations, we need to include more DM particle to construct DM packing. These two factors jointly result in the situation that the simulation for the 3D require more intensive computation, and also it demands a larger memory usage. This challenge requires us to propose a very high performance solver so that it can handle the intensive computation, and also we need to deploy it in a distributed system so that it can handle or accommodate the larger memory use. Yep, as the DM comprise the majority of the computation, so that we will use different parallel strategy for the NPM and the DM. For the NPM, we will use the high performance solver called CPGO NPM, and only use the multi-thread parallel computing. While for the DM, right, we will use the YARD and use the multi-node parallelizations. This figure shows the parallelization scheme for the multiscale modeling, which is based on the flat NPM model. Once the NPM get the deformation for all packing, it will be scattered to different NPM node. Then NPM node will share the packing locally so that it can avoid the frequent data formatting and data transfer between different nodes. To fully unleash the capacity of the proposed parallelization scheme, we will also implement our code in the TNR2 supercomputer and do the simulations. To evaluate the performance of our parallel scheme, we will conduct a strong scaling performance test, which could be up to 500 nodes. This figure indicates that with the increase of the invoked load, the DM cost will reduce linearly. However, the communication cost for the MPI will be increased correspondingly. The overall performance is shown in this slide. As you can see, when the invoked node is smaller, it's not that large, like a smaller 100 computer, and it will reach, is quite close to the ideal speed up predicted by the Amando laws. However, if we further increase it, the performance will not increase. This is due to the communication cost increase is larger than the reduction in the DM cost. With that effective parallel scheme, we can try to conduct some 3D modeling. The most easy 3D application is the column collapse. In this case, two columns will be modeled and their aspect ratio will be equal to 0.6 and 2.4. And in each column, it will comprise over 60,000 RVE, and each module and each packing will contain over 800 DM particles, which means that the simulation could involve up to 50 million DM particles. Here is the animation for two cases. This is for the smaller aspiration column, and this one is for the higher aspiration column. We can also extract the particle rotation for the for each material point. Due to the friction by the side wall, the particle close to the side wall will subject to different rotation as indicated by the different color in this contour. Another interesting example is the intrusion of the solid object. In this example, we will prepare our soil domain and then push the solid object with different cross section into the soil. And also, this case is quite large and it will take around 40 hours to simulate. This is the simulation result and showing the displacement. And yep, as you can see, in front of them or just underneath the solid object, there will be formed a rigid zone, which just like penetrating into the soil as whole body. And this shows the contour of angular velocity. And as you can see, in the boundary of these active zones, it will have a very large angular velocity. While for those soil underneath the soil, underneath the soil intruder, the angular velocity is not that large. On the right-hand side, it shows some selective packing for string during the whole simulation. And the horizontal axis shows the displacement indicating different stage of the loading. On the right, the vertical axis shows the selected RVH location. As you can see, as the compression continues, the packing on the top will be compressed first and then gradually propagate downward. For this case, another very interesting thing is the response by the intruder. This paper, Nature Communication, proposed that for this kind of problem, after some normalizations, the reaction force and the normalized displacement can be quantified by a very straight line, and the slope of this straight line only have one dependent parameter, which is the friction angle of the soil. As you can see, after some normalizations, the packing with different cross-section shape will collapse into just one line, which is agree well with the prediction by the Archimedes law, modified Archimedes law developed by this paper. Yep, so far, all the DM packing we use is sphere. However, in reality, the particle shape could be irregular, just like this figure shows. In DM community, there are several methods to model the non-spherical particle, such as the clouded particles, super ellipsoids, and even the more advanced level set base. In current study, we're just using the STU DM following the super ellipsoids to model the non-spherical particle. Here, the STU DM is mainly developed by the Shi Wei Zhao in Hong Kong UST. And why I choose that? Because it just using the super ellipsoid so that it could have a very good balance between the particle shape and the efficiency. Another reason is that this software share a very similar function interface with YARD, so that we can shift between the YARD and the STU DM smoothly without any difficulty. As an example, we are going to model the footing problem on an isotropic soil. To capture the potential asymmetric failure pattern, we will use the full domain to model the problem. And to model the inherent anisotropy soil. Here, we're just using the ellipse particle to generate the RVE by just changing the bedding angle so that we can generate different inherent anisotropy particle. And this figure shows the particle orientation. As you can see, for the random one, its particle orientation is evenly distributed along each direction, so that we can also assume that this packing can be viewed as an isotropic packing and can be compared as a reference. Let's look at the bearing capacity. This figure shows the bearing capacity factor and its relationship between the bedding angle. Several conclusions we can make. First, let's look at the random one. For the random one, we can see that the multi-simulation result agree well with the Pareto series, which is developed based on the isotropic soil assumptions. While for the rest one, it has a very large variation. This is also due to this prediction rely on isotropic soil assumption, which cannot be hold for the anisotropic one. And the bearing capacity is found to be generally decreased with the increasing bedding angle. Here is the comparison between the isotropic packing and the anisotropic packing. On the left-hand side, it shows the isotropic packing. And on the right-hand side, it shows the anisotropic packing. As you can see, for the isotropic one, the failure pattern will become symmetric, while for the other one, it will be asymmetric. Yeah, we also compare the contour for different bedding angle, and we can see for the packing with maybe zero bedding plane angle and the horizontal one, or the isotropic one, its failure pattern will be symmetric. For all the rest one, their failure pattern are asymmetric, and the alpha equal to 16, RV holds the largest asymmetric pattern. Okay, the second part of my presentation is the multi-physics extension for the multiscale approach. Sand is quite mystical materials. As you can see, if the sand is totally dry, if we just put it on the ground so that it will collapse and form a sand pile. However, if we add some water so that we can just using that wet sand to build a sandcastle here, and also in many other applications, we will involve geothermal energy and also the hydrate dissociation. All these scenarios require us to extend our multiscale approach to the multiphysics region. To begin with, let's look at the hydromechanical coupling. The multiscale framework for the hydromechanical coupling can be shown in this diagram. We will just using the one-point multiphase material point to do the macroscopic simulation, while for the solid part, we will just using the DM to replace its solid skeleton response. This framework is established based on the Tasaki principle of stress. In terms of the governing equation, we're just using the UVP formulation, which consider the acceleration for the solid phase and the fluid phase simultaneously. With the governing equation, the last step we need to do is do the temporal discretization. Many options we can take. The most easy one is the explicit MPM, which means that we can just using the previous steps velocity and also the stress and the water pressure to compute the next step. For the explicit, it's quite simple and easy to understand and easy to implement. However, for the soil or for the soil here, the water is assumed to be weakly compressible, so that its time step is governed by the bulk modulus of the fluid phase. Another discretization format we can take is the semi-implicit explicit MPM. For this one, we just using the previous steps constant stress and using the current steps power the pressure to solve the momentum equations. As you can see, for this type of discretization, it will result in a very highly coupled formulations. To solve originally, if for the semi-implicit one, we need to solve the velocity and the power pressure simultaneously, which is quite challenge in mathematical aspect. However, we could also using the fractional step by introducing some internal variable so that we can just solve the power pressure and the velocity one by one, so that to reduce the compressivity for the whole equations, as you can see. And here, this is the unmodified one. We can just split this equation into two, by introducing the intermediate solid velocity and the intermediate fluid velocity, so that these two can be decoupled. And after some arrangement, we could obtain a Poisson equation, which solving it, we can obtain the power pressure increment. Yep. After some arrangement of the equation and some tedious algebraic operation, the whole solution procedure can be classified into 3 steps. The first step is solving the intermediate velocity. The second step is solving the power pressure. And the final step is correct the intermediate velocity to obtain the final velocity. Yeah, get rid of all this complicated formulation. The only conclusion we need to know is the semi-implicit permit a permeability independent time step, and which is at least one order larger than its explicit counterpart. To validate the proposed two-phase multiscale framework, we will conduct a 1D consolidation test for benchmark. In this case, we will attach a DM packet to each material bond here and do the compression. We also extract the elastic parameter for this packing for very small string range, so that we can compare the solution to an analytical solution. Here is the benchmark result, which shows that our power pressure agree well with the analytical solution, as well as the degree of consolidation. Another example is the cyclic shaking. Here is a container. Then we can put the soil here inside this container. Different packing will be generated. Similar as the previous one, we will generate the medium dense one and the dense one packing. During the loading, we could just shake this container from left to right and then right to left according to the prescribed velocity. And here, this figure shows the dropping pulse response from A, B, C. And as you can see, the packing with different initial relative density has different cycle resistance. For the dense one, even in the later stage of the loading, the packing does not exhibit any signal about liquefaction. Another case is the saturated column collapse. This is the simulation result for the power pressure. As you can see, initially after the release of the column, negative power pressure will be generated due to the tendency to enlarge its volume for the soil domain. However, this power pressure will be gradually dissipated and then generated a positive power pressure due to the gravity of the soil. If we compare the saturated soil with the dry case, we found that for the saturated one, it will have a slower development and has a very longer duration for the whole flood process. A more complicated case is the wave propagation in anisotropic saturated soil. In this case, we will apply an impulse load at the top center. Then it will generate wave, a stress wave, and then propagate it to the boundary of the domain. In this case, we will also prepare different packing. One is the isotropic packing. Another two is quite regular packet packing, has the bedding angle of 0 and 30. This animation shows the stress wave propagation, and this one shows the pore water pressure. As you can see, for the isotropic packing and isotropic with the bedding angle equal to 0, they will generate a very symmetric wave propagation pattern. While for the other one, for the rest one, the wave propagation could be asymmetric. We also analyze or investigate the influence of the permeability. This figure shows the surface center settlement. As you can see, if we are using more larger permeability, then it will subject to a larger settlement when applying the impulse load. The right-hand side shows the surface displacement evolution, and one conclusion we can draw is that with the permeability decrease, the wave will be preserved more nicely, and the wave will be dissipated less apparent. Okay, that's it for the hydromechanical coupling. To make the whole story more complete, I also wish to introduce some of the collaborative work in other physical field coupling. The first one is the thermomechanical coupling, which is mainly done by Shiwei Zhao in USD. Similarly, in the microscopy, if we consider the balance equation for thermal by the equation of energy as well as the momentum equation, and consider the particle scales, thermal expansion, and the thermal sensitivity bond, so that we can model the thermomechanical coupling behavior of the granular media. Here is animation or the simulation result for the melting induced column collapse. On the top, it shows the column collapse without considering the thermomechanical coupling. And just as the dry one, it will collapse like that. And if we consider the thermomechanical coupling, the failure pattern or the failure mode will be more ductile, and its final deposition profile is totally different from the previous one. Another step further is the thermohydraulic and mechanical coupling, which is mainly done by our colleague Ji Du-Yu in UST. In the THMN coupling, we not only consider the thermal part. However, and in addition, we also consider the hydraulic and the mechanical coupling through the mixture theory. And while in the mesoscopy, we not only consider the kinematic of individual particle, but also consider the isomatic soil bond, which is temperature sensitive and even the pressure sensitive. We implemented such feature. We can also model the thermohydraulical coupling for the soil. This example shows the freezing thaw behavior of the ice-bonded granular media. In this soil domain, we will just apply a boundary condition here, and then make its temperature variated between -5 degrees to 5 degrees. And this is the animation result showing the different fields contour. And this one line shows the zero temperature line. As you can see, as the number of the free short cycle increase, the ice line will be gradually propagated to the side wave. Okay, that's it for the. Let me just quickly conclude our presentation. In my presentation, I just introduced the hierarchical multiscale modeling, and this approach provides a rigorous but effective means to bridge the micro, measure, and the micro scale of the granular media. And also, the multiphysics extension could be further unleash the potential of the multiscale approach in a wider scenario. Okay, that's it for my presentation, and thank you for your listening.
Thank you, Dr. Liang. We will now proceed to the Q&A session. Please feel free to leave a message to the chat room if you have any question regarding the webinar. We have one question. Please inform the use of these techniques for the civil and geotechnical projects.
Yep. Very, very good questions. Yeah, as you may know, the multiscale modeling is still in its very early stage of development. So we only noted that the first multiscale modeling paper was published no more than 10 years ago, and it's quite unmeasured so far. According to my knowledge, no practical application are adopting this multiscale modeling, but this is what we are putting effort to do in our future.
So if there are no other questions, we're going to the close of today. Thank you, Dr. Liang, as the speaker of today's webinar. We have prepared carbon credit certificates for you as a token of thanks. I'm sure all of us have learned a lot tonight and hope you have enjoyed the webinar. The digital attendance certificates will be sent to your email in 4 weeks. Once again, thank you very much for joining today, and we wish you a good evening. See you all again in future events. Goodbye.
Yeah, thank you, Fiona, and thank you, everyone.